And we're going to title our notes section 10.1 and 10.2. And we're just going to start with vocabulary right away. And we've got a decent amount of vocabulary to get down, so please make sure you're taking really good notes and you are drawing the pictures when we need to. Okay, first thing we're going to do is just define the word circle. Well, what is a circle? A circle is defined by the set of all points equidistant from a given point in a plane. Now, when we say in a plane, what we're referring to is just a two-dimensional set. All right, so if all points are equidistant from a given point, that point in the middle we usually call the center. Now, we don't have to use the letter C to represent center. We could use any point, but a lot of times they do use C because it's a nice name for a center point. And then radius, you're probably familiar with radius. Radius officially is the segment that goes from the center to the rim, or the center to the circumference. Now I actually have 3 different radii drawn in here. I'm going to highlight this one. And it's just the distance from the center to the circle is considered a radius. So I'll give you a second to get caught up, draw that picture, because then we're going to introduce a couple of new pieces that you may have not heard of before. Okay. So now let's go ahead and take a look at something you may or may not be familiar with. Um, it's called a chord. So what is a chord? A chord is a segment, so part of a line, with endpoints on the circle. Well, there's 2 chords identified in this picture. I'm going to draw this one. And this chord, you can clearly see that the endpoints are on the circle itself. But we also have another chord in this picture, but it's a special kind of chord. The blue chord that I just highlighted goes through the center. So it's a segment that has points, endpoints on the circle, but it goes through the center. That's a special name that we're going to call diameter. So notice how we defined that. Diameter is a chord. Right? It's still a chord, but it goes through the center, and that's what makes it a special point. And we know that the diameter is made up of 2 radii, because in the same circle, all radii are congruent. But the diameter is a special kind of chord. Now let's look at these pieces here. And this is pretty important, not just for geometry. We actually use this idea in calculus, pre-calculus. It comes up quite often. So hopefully you have a strong connection to our definition of secant and tangent lines today. All right, what is a secant line? Well, a secant line is a line that intersects the circle at 2 points. So let's think of that. Secant line, right? A line goes on forever, and it intersects the circle at 2 points. And you can see that is definitely true here. So I'm going to call that a secant line. Now I will mention that we are going to do a lot more with secant lines. And there's a lot more that we're actually not going to do as well. So it's important to understand what a secant line is, but also realize that there's a lot more to it. All right, a tangent line. What is a tangent line? Well, officially, a tangent line is a line that intersects the circle exactly at 1 point. So I'll use this green line as an example. Right now, if I take the green line the way it is, that's just another secant line. It crosses at 2 points. So what if I change one end and I keep moving it until I don't intersect the circle at 2 points, but I intersect it exactly at 1. So here's an example of a tangent line. And there's something special about the point at which it intersects. So this blue point where the tangent line hits the circle is called the point of tangency. And the line itself is called the tangent line. And we're going to explore some properties on what is true when a tangent line intersects a circle and how does that relate to some theorems that we're going to be learning. You don't have to draw the picture that I have down here. I just want to show you one thing really quickly. I know we call it a tangent line, and a line goes on forever, but it really doesn't have to be a tangent line. It could officially be just a ray as well. So in the picture that I drew on the bottom here, you can see I have a circle. I have my blue point of tangency where this line touches the circle. But if I was to continue that line, notice how that line does not go into the circle. So this is an example of a tangent line, or just we would call it a tangent. All right. I do want to note if I drew it this way, notice if I drew this line and continued it on here, it would be a secant line because it would cross the circle at 2 spots. So the blue line is not tangent even if it stops right here. So even if it just goes like that, yeah, it touches the circle at 1 point, but if it was extended, it would eventually turn into a secant line. So a tangent can only go and touch the circle. Basically, a tangent line can't go through the circle, otherwise it would be considered a secant. Okay, really quick, Tyson, I sent you a chat. Can you please read that chat and respond to me? All right, next two we have theorems. Definitely write these down. And whoops, there we go. And I actually want to start with the picture because I bet you are going to be able to make a conclusion based off of this picture about this potential theorem. So let's just explore the picture right now and see what do we have. Well, we have a tangent line. It's a line that touches the circle exactly at one point. And then we also have, it should tell us that this is the center, but we have a radius. So if, okay, thank you, Tyson. If we have a tangent and a radius, the way that these two interact is always going to be the same at the point of tangency. And what it says is if the radius and a tangent line come together at a point of tangency, they meet to form a 90-degree angle. So the tangent line and the radii are perpendicular. Now, I'll just mention this. I don't really care that they call this theorem 10.1. I just care about the fact that you understand that when you see a radius and a tangent, it meets to form a 90-degree angle. So in a plane, a line is tangent to a circle if and only if, that's that funny spelling of if and only if it is perpendicular to the radius at the point of tangency. So that's our conclusion, is if you know it's tangent and you have a radius, that has to be a 90-degree angle. And vice versa. If it's a 90-degree angle, and you know it's a radius, then you know that this line has to be a tangent line. All right, the next theorem. Let's analyze the picture first before we show you the theorem. So if I look at the picture, what do we notice? We have 2 points of tangency, and I have 2 tangent lines. A tangent on top and a tangent on bottom. And they both intersect the circle at one point, but those tangent lines actually meet at a common point. And what happens then is the distance from the point of tangency to that common point is the same distance on both tangents, which means these two lengths are congruent. So that's what this theorem is stating. It's called the two tangent theorem. Two tangent segments from a common point are congruent. So notice it's from the point of tangency to the common point. That distance is the same on both tangent lines. I will post these notes so you can go back and look at them as we go. All right, you definitely want to write this problem down and draw the picture as accurately as possible. It says find the radius of the circle C. So I got to find the length of R, the red R, if point B is a point of tangency to the circle. So I'll give you a minute to write this down, and then we are going to solve it together. And I'll just say, leave yourself a little bit of room because there's a good amount of algebra here that we're going to have to use and work through. All right, let's take a look at this. And I'm going to actually draw an extra little picture here that's not really needed, but I think it might help you visualize what's going on. So here's the way I interpret this problem. The directions tell me that point B is a point of tangency, which makes AB a tangent line. And then we know this is a radius. So from the theorem we just had, if it's a radius, and a tangent line, we know that those are perpendicular, so I have to have a 90-degree angle right there. So what I'm going to do then is look at this as a right triangle. But what I want to do is I just kind of want to redraw this so it's positioned differently. So AB is 80 feet, right? And then I've got the length of 50. Oh, not great. Then I've got the length of 50. But then I have an extra little r, right? And then I've got another r down here. And if I was to draw this accurately, these two red lengths should be the same length. So what do I know? I know that this length from AB, from B to C, is r. This red length is r. And the blue length is 50. But I don't want to write it as 50 in r. The whole reason why I wanted to rewrite this was so I could come up with one expression for the full length of AC. So that's what I want to look at here is, notice the distance from A to C is 50 plus r. Or you're going to maybe see why I would actually rather write it as r plus 50. And then we know that this is a 90-degree angle right here. So I just redrew the triangle so it's not as confusing. But now it's just a special kind of Pythagorean theorem problem. So what we're going to do is we're going to take Pythagorean theorem and we're going to follow c squared equals a squared plus b squared. It doesn't matter which one I call a or b. Let's call, just for fun, let's call this one a. Let's call this one b. And the hypotenuse is always c. And just to make it even more easy, I'm going to get rid of a, b, and c there, the endpoints. So here's the whole reason why we're doing this problem. Notice when I plug in c squared, I get r plus 50, and then I have to square that whole thing. There's a reason why I put it in parentheses. And then a squared ends up being 80. 80 squared plus b is our length r, so r squared. All right? So we just used Pythagorean theorem, but the reason why we're doing this problem is right here. This is really just to practice our algebra skills. And I'm going to just put a careful little note here. This is the error, or the most common error in this problem is right here. How students interpret r plus 50 squared. So when I think about this, I need to think about what does it mean to square anything. I'll just say, what does it mean to square something? Right? Well, let's think about it. If I asked you to say, what is 3 squared? You probably memorized it, and you'd say 9. But why? What is 3 squared? 3 times 3 is what gave me 9. What's 10 squared? Well, 10 squared is 10 times 10, which is 100. So we have to think of the meaning of squared. Okay? And that's what's going to allow us to make this next move. So what is r plus 50 squared? Well, it means r plus 50 times r plus 50. All right, now we have to interpret this a little differently because I'm multiplying two binomials together. And you might remember to multiply binomials, you FOIL. Now you can do the box method, and I'll show you that after this, but I recommend FOIL here. So we're going to take r times r. That's your first terms, and the O in FOIL is your outer terms. So r times positive 50, I like to write that as 50r. And then we have the I in FOIL, that's the inside terms, 50 plus r. Trust me, 50 times r is plus 50r. And then the L stands for the last terms, 50 times 50 is 2,500. But then you'll notice you do have the two like terms in the middle. So I'm going to add those up to give me 50r, and 50r is 100r. So I get r squared plus 100r plus 2,500. That's what r squared plus 50, r plus 50 squared turns into. And that is the number one error in a problem like this, is students just don't understand what it means to square something. Once they write this step, they usually FOIL well and get everything the way they need to. All right, now we're not done though, right? Because our job is to actually take all the rest of the pieces. So 80 squared, I'm just going to bring this all the way down instead of rewriting it. 80 squared is 6,400. Plus, and then don't forget about the r squared. We're just going to write that as r squared. All right, so now I have everything expanded out as far as I can go. And now it's just algebra. I need to move all the r's over to one side, but I have an r squared on this side and an r squared on this side. So if I was to move an r squared over from one side to the other, something really friendly happens here. Positive and negative r squareds, those add up to 0. The r squareds go away completely, and now all I'm left with is 100r plus 25, 100 equals 6,400. So in that case, I'm just going to move this 2,500 over here. If I subtract 2,500 from 6,400, I end up with 3,900. And then if I divide by 100, I get my radius at 39. All right, so now officially this is 10.2 notes. Everything we did prior to it was 10.1. This is 10.2, and 10.2 focuses more on arcs and angle measures, and that's what we're going to do here. Is we're going to define kind of the difference between a central angle and an arc. All right, so I'll give you a second to write this down, and I'll explain it as you guys are writing it. So a central angle. What is a central angle? Well, officially, a central angle is based off of that word right there, the center. It has to be based off of the center of the circle. So any angle with its vertex at the center of the circle is considered a central angle. For example, angle ABC is a central angle. So it's the angle that's formed between the two radii at the circle. So that's what's considered a central angle. Now in a couple minutes, we're going to talk about how to find the measure of that angle and how the measure of that angle actually relates to the arc. And the arc is what's considered basically it's a portion of the circle, or some people say it's the portion of the circumference, right? So it's a certain part around the circle, but it's part of the circle between the two endpoints A and C. I'll let you guys get caught up here. Okay. So we know that a central angle is the angle that's formed between the two radii and the vertex is at the center, and the arc is the part of the circle that's formed by the two endpoints of the radii. Now, because we know what an arc is now, we can actually define the different types of arcs. So in this picture right here, we don't know the exact angle measure, but I know for sure that this arc is less than 180 degrees. And the reason why is if it was 180 degrees, then that would go halfway around the circle, and this is definitely less than halfway around the circle. So we would call the arc from A to C a minor arc. And a minor arc is an arc that is less than 180 degrees. Put my little degree symbol up there. And then how would we write that, right? Geometry is full of symbols. So one way to write this would be to take the endpoints from A to C and then just put a little arc symbol over it. So when you see A to C, that A and C are the endpoints. And then because there's just two letters, it's the closest distance between them. So it would tell us to go this way around the circle from A to C. Now, we can flip that around as well. I could call it C to A and go the other direction, and that's still a minor arc. A major arc is an arc that is greater than half of the circle. So it's greater than 180. Now we have to be careful here. If I was to go the other way around the circle from A to C, that's definitely more than 180 degrees, right? But I have to be careful because I can't say A to C. There's a problem if I say A to C. The person reading this wouldn't know if I wanted it to be a major or a minor arc. So that's why we need an extra little point, and that's where the point D comes in. I'm going to start at A, and I'm going to go through D and end at C. So when we name major arcs, we need 3 letters. The 2 outside letters are your endpoints, and the letter in between tells me the direction to go. So if I read this, it would say start at A, go through D, and all the way to C around the circle. Right? So notice, it's not an angle because there's not an angle symbol. The little arc above refers to the arc measure. Now we could also name this CDA because that would just tell me to start at C, go through D, and around A. But both of those measures are definitely greater than half the circle, so therefore they are both considered major arcs. All right, and then a semicircle is a circle that is cut in half, right? Well, an arc is if it's exactly halfway around the circle, we consider that a semicircle. So it's an arc that is an exact 180 degrees. And I don't have a great picture for this. You'll see on the next slide. If AC was the diameter, then you could say A to C, and if it went exactly halfway across, it would be a semicircle. You'll see on one of the next slides coming up how we would name that. All right, so those are the types of arcs: minor, major, and semicircle. And it is based off of the degrees, but how do I measure an arc? Right? How do we know that what the degrees are? And that's what we're going to talk about next here. The measure of an arc. I don't know why this did what it did here. There we go. How do I measure an arc? Well, The measure of an arc is the exact same measure as its central angle. So let's say I've got an angle TED. The measure of the central angle TED is, and if we had a protractor, I would actually have you measure this, but since we don't, I'm just going to say this is 98 degrees. Now notice that's the central angle. So the arc now, how would I write the arc here? That's one thing to think of. The arc is the distance from the end point to the end point. So I could say this arc TD is equal to the same measure. So if its central angle is 98, then its arc measure is exactly the same. Notice the differences. And by the way, this little m that I put in front here, if you remember that, this little m stands for the measure of angle TED. So that referred to the central angle. And then the arc is just the distance between the endpoints. And those are exactly the same. Now I will mention that there actually is one more arc and one more angle that we could discover here. So let's say I just put a random point R right here. I could actually find a couple other things. What is the measure of DRT? Oh, I don't know what happened there. Well, we know that if I start at D and I go through R to T, that has to be everything but the 98 degrees. Well, we know a circle is 360 degrees, so if I subtract the part that I know, that's going to give me the part that I don't know. So if we subtract that, that should be 262, I believe. Which, notice, if I know that arc, then I don't have any other work to do, but I actually know this central angle is 262 as well. So that's how we measure arcs. Okay, let's go over this one quick. You may or may not have had enough time to get it done. But here's the way I like to approach it. So we have to find the measure of the four arcs that are given below and then classify them by their size given the one central angle BEC is 135. So a couple of things we can do. As soon as I know a central angle, I know the arc that is made up of those two radii is the same measure. Right? So that answers the first question. BC, the arc BC is 135. Since that is less than 180, that's considered a minor arc. All right, so then I got to find AB. Well, the arc AB has to be the same as this angle measure here, but there's one fact that they didn't tell us that we need to interpret. Notice how AC is a straight line, it's a chord that goes through the center, which makes that a diameter. So that means that AC has to be 180 degrees. Now you could just take 180 minus 135 from the arc and figure out that this is 45 degrees very quickly, or you could see that these two lines make up a linear pair. and the central angle is also 145. So this arc AB is 45 degrees, and since that is less than 180, that is a minor arc as well. All right, and then the next one, actually the easier one might be AC. Now notice they don't tell me which direction to go. Do I go this way or do I go this way? It doesn't matter because AC is a semicircle, so either way it's half of the circle and it's going to be 180 degrees. And we know that because AC is the diameter. All right, and then the last one is actually introducing something that's on the next slide. It's called the arc addition postulate, which basically says if you know AC is equal to 180 degrees, then BDC, starting at B, going through D all the way to C, so this arc here has to be the sum of the green arc plus the red arc. So one of the postulates that we're going to talk about is you can add two arcs together to get a larger arc. So the measure of BDC is 225, and since that is larger than 180, that's considered a major arc. Okay. All right, this last slide, I actually don't want you to write. Some of it is common sense, and some of it we just need to address, but we're not going to take the time to write it. So here's what we got. Something called adjacent arcs. Well, we've talked about adjacent angles before, so I just want to quickly show you what is an adjacent arc. Well, let's picture this red arc here. An adjacent arc would be an arc that shares a common endpoint. So let's say that the red points go from here to here, and then if I draw another arc, it would be adjacent if they share a common endpoint. So here the red and the green is a common piece, so those would be common arcs, or adjacent arcs, excuse me. So let's say, just for fun, that this is 40 degrees, and let's say that this one is 100 degrees. It's not, I'm just kind of making this up, but what does that mean? That means I could add the two arcs together to get a larger arc of 140, and that's called the arc addition postulate. It just says you can add arcs together to make bigger arcs, or you can even subtract arcs to get smaller arcs. Okay? And then the last one is congruent arcs. If arcs are congruent, that means they have the same measure. However, we have to be really careful when we say that. Now, I'll say this, we're not going to do a lot with congruent arcs, but I just want to paint the picture for you. So arcs that have the same measure are congruent, but they have to come from the same circle or congruent circles. So let me just show you a quick visual of this. Let's say I've got an arc here, and I've got a circle that looks like this. Okay, so here's my central angle, and in that central angle, I've got this arc, which is, I don't know, let's call it 90 degrees. All right, now, if I had another circle, let's say here, and I knew that these two angles were congruent, then the blue arc would be congruent to the red arc because they're both 90 degrees and they come from the same circle. But that's not necessarily true, because watch what happens here. What if I move this over here, and then I get rid of this part here? Now, are these two arcs still congruent if I make this one a little bigger? All right, well, let's look at it. They have the same measure. This is still 90 degrees. You can see if I match this up, notice how that central angle is just exactly the same. So they have the same angle measures, so this is 90 and this is 90. However, I cannot confidently say that these are congruent. So I'm going to get rid of that congruent symbol. And the reason why is look at how long this arc is. It's not the same arc as this one. So that's why these circles have to be congruent. And the way we would tell if the circles are congruent is you would need to know something about the radii. This radius would have to equal this radius here, but since this radius is much longer than this one, these two circles are not congruent, which means this arc, even though it's 90, is not congruent to this arc. So we're not going to do a lot with that. I just wanted to share that with you quick. Okay. Really quick, I want to mention something about homework. We kind of noticed some trends here, and we want to just review the expectations moving forward for the rest of this year. So you are expected to attempt all problems that are assigned to you. You are expected to draw diagrams when necessary. Complete work is shown, including equations, algebraic work, and then your answers must be, your numeric answers. And then here's the big part. If you only put the answers down, you'll receive 1 point. And I shouldn't even give you a point because I post all of the answers with the worked out solutions. So if you're just copying the answers, I don't know if you're doing it. I don't know if you're copying them. I'm not really sure. So I'm going to give you 1 point just because you put in some effort. So you get 1 out of 5 points. You must show work. Now on tonight's homework, it looks like a lot of problems. Here's the work for tonight. A lot of these are vocabulary. And if you're just staring at a picture and you're not interacting with it, I don't need to see the drawing of the picture. But in the example we did where we added stuff to it, that's an example of how you should model your work and show your work. Draw the picture, add an arc in or add an angle measure in to help you solve the problem. That's what we need to see. All right, so hopefully that gives you a little bit of an idea of what we're expecting. Your homework tonight is right here. When you're done, you're going to submit that to Schoology. Okay, we have 15 minutes left of class, and what I'm going to do is I'm going to give you a link, and this link is a video. So if you open up the chat right now, there's a YouTube video. I think it's 12 minutes long. You need to watch it because it's about electives and it's about registering for next year's classes. And like I said before, freshmen and sophomores, you guys don't have a lot of opportunity to take electives. You could take a couple, but not a ton. It's when you get into your junior, senior year that you have more availability in your, or more flexibility in your classes that you could register for more electives. But go ahead and watch that video. And the expectations for tomorrow in class is you're taking all day to register for your classes. All right, so watch the video, do the homework tonight, and that's all I have. If you guys have any questions, feel free to stop into my office hours and I can help you out with anything that you need.